Hello everybody, and welcome back to another geometry lesson. Today, section 5.6, proving triangle congruence by ASA and AAS. So we've talked about a lot of different theorems throughout this unit on how to prove that two triangles are congruent. We've got two more, and then we are going to review what we've learned. So the first one we're going to be learning today is the angle-side-angle congruence theorem. And it basically says this, if I was to draw a diagram here. Let's say we have two triangles that we want to show are congruent. Well, the way you can do it is by showing that they both have a congruent angle next to a congruent side length next to another congruent angle. And by showing that we have those congruent pairs, we've shown that these two triangles are congruent. This is what the angle-side-angle congruence theorem tells us. If two angles and the included side of one triangle are congruent to those on another triangle, the two triangles are congruent. If two angles and the included side, what do we mean by included side? That just means the side in between those two angles. It's like a sandwich of angle, a side, and angle. If two angles and the included side of one triangle are congruent to those of another triangle, the two triangles are congruent. Perfect. The last theorem that we are going to be learning is the angle-side congruence theorem, which, based on the order of the letters, you can tell is very similar to angle-side-angle, but it's just slightly different. Let me show you what I mean. If I have two triangles here, and I wanted to show they were congruent by angle-side, what that means is we have a congruent angle. The next thing we have is another congruent angle. And then we have our congruent side. The order of the letters here tells you the order of the congruent parts on the diagrams. If this happens, then the triangles are congruent as well. So very similar, the only difference is instead of the side being in between the two angles, it's not in between the two angles. So by the definition, we would say if two angles and the non-included side of one triangle are congruent to those of another triangle, the two triangles are congruent. Note this time we talk about the non-included side, which means the side that's not in between the two angles. As long as you have two angles and one side, you can use one of these two theorems to prove the triangles are congruent. So let's go back through all of our theorems and see if we can recall all the different ways to prove that two triangles are congruent. So today we learned that two triangles are congruent if an angle, side, and angle are congruent, or if an angle, and side are congruent. But there are four other ways we can prove that triangles are congruent. Here's the list. Last class, we talked about two theorems. Hypotenuse leg, which only works on right triangles only. We also had the side, which works on any triangles. The class before that, we had side, angle, side. side angle side was our big one. And then in section 5.2, the last one is we proved that if all corresponding parts are congruent, then two triangles are congruent. So 6 different ways to identify triangles as being congruent. If you can find any of these on a pair of triangles, they are congruent. But I did want to remind you that there are 2 that do not work out. So these are 2 theorems that don't exist. One of which is the angle congruence theorem. Does not work. Why? Because you can have 2 triangles with all the same angles, but just have them be different sizes. The angles are all the same on these, the sizes are not. The other one is SSA. And the way that I remember SSA is you don't want to accidentally spell it backwards. SSA and its backwards variation are not theorems that we can use to prove 2 triangles are congruent. Those are the only 2 that you cannot use. All right. If you can't show that one of these 6 congruent statements works, the triangles are probably not congruent, or at least you're not able to show that they're congruent. So I want you to take a look at example 1. I'll show you the first one, and I want you to see if you can do the second and third. It says determine whether the triangles are congruent or not, and state your reasoning. As I'm looking at the triangles on part A, I see that these are both right triangles. So immediately my brain starts thinking, this could be hypotenuse leg. I'll give you a spoiler alert, it isn't, but it's a reasonable thing to think that if it's a right triangle, we can use hypotenuse leg. So we got an angle that's congruent because of the right angle congruence theorem. So we got an angle. We notice that there's a congruent side here as well. GF is congruent to GD. So we know that that's congruent because it was given to us. But when we start thinking about it, we need one more piece of information in order to show that these triangles are congruent. The key is with this center part here. These 2 angles are vertical angles. So if we look at our diagram now, it goes angle, angle, side, all in order. Is there a theorem that says this? That if we have an angle, and a side, they're congruent? Well, yeah, it's the angle, side congruence theorem. So we say yes, because of AAS. Pause the video and see what you can do with parts B and C, and we'll talk about it in just a moment. Hopefully you've had a moment to try these out. Let's take a look at part B. So in part B, once again, we are given a pair of sides that are congruent. That's convenient. Now, we need to find more information before we can tell if these are congruent or not. So my first thought is to immediately look at line segment QM. Notice that QM is the right side of this triangle, and QM is the left side of this triangle. So even though it's the same line, we're thinking about it as 2 different sides. We can use the reflexive property anytime this happens. So we do know that we have another side due to the reflexive property of segment congruence. Love it. But if we're looking for one more piece of information, it's kind of tough. We might look down to these 2 angles here to say, oh, these look like right angles, but is there anything that would tell us those are right angles? Not really. They look like they're right, but we can't prove that they're right angles. Well, there is one more thing that we can see. Let's say I covered up line segment QM here. What type of triangle do we have? It's a big triangle with two congruent side lengths. The big triangle, QPR, is an isosceles triangle. So at the very least, we know that any isosceles triangle has congruent base angles. So we got an angle pair due to the base angles theorem. But what do we have here? A side, and an angle. That's actually one of our not theorems. Believe it or not, we cannot prove that these two triangles are congruent. Not enough info. Finally, for this one, C, we do have some information that can help us. For instance, we are given that these top angles are congruent, so we got a pair of angles that are given. And we've got another pair of angles on the bottom that are congruent. So these two are also given. In between them, we notice that there is a congruent side here because of the reflexive property. Side MP is congruent to side MP. So we could use the reflexive property of segment congruence to show that an angle, a side, and an angle are all congruent. That's just the ASA congruence theorem. So we are done. Let's flip to the back side and see what we can do there on page 12. Here we have a couple of proofs, and with any set of proofs that you do, actually trying out the proof, trying to see how well you do, maybe doing well at it, maybe not doing well at it, that's the best way to practice. What I will say is this first proof could be done in 4 steps, or I've seen one student do it in 3 steps, which is crazy quick. But 4 steps is pretty much what we're going to be expecting. Exercise 3 is going to be in 5 steps. If you want to practice proofs, pause the video, try to see what you can do with a pencil, and then come back in a moment to see what I would do with these proofs. Pause the video now if you want to give these a shot. If you already gave them a shot, or if you really didn't want to give it a shot, that's okay. I'll show you how to do these proofs here and now. So for this first set of triangles, we know 2 things. BD is congruent to BC. That's actually something that's marked off on our diagram as well. So we have a pair of congruent sides. And we're also told that AD is parallel to EC. These are our givens. Now be careful. Just because AD is parallel to EC does not mean that they're congruent. So it's not like we have a pair of congruent sides here. They're just parallel. My recommendation is always to start with your given, but many of you probably identified something else from the diagram. A lot of students, first thing they see are these vertical angles. So let's show that first. Anytime you have 2 sets of straight lines crossing each other, you get vertical angles. So this left angle and this right angle are congruent. What do I call this left angle? Well, I'll need to use 3 letters. I can't just call it angle B because angle B could be any of these angles. So I'm going to use 3 letters, and I'm going to call it ABD. Your vertex has to be the middle letter. So I'm going to say angle ABD is congruent to. Now, as we look at the other side, remember, you can always look at your proof statement to see what each letter matches with. A is congruent to E, for instance. So it's congruent to E. B is congruent to B because they're both in the same spot. And D is in the same place as C. So I'm going to call it C. This is the vertical angles congruence theorem. There we go. From here, we can then use our given. We're told that 2 lines are parallel. Whenever you are given parallel lines in this unit, think about these two parallel lines as two lines cut by a transversal. I'll show you an example. If I treat this as a transversal, take a look at what we have. We have two lines cut by a transversal. That's going to create alternate interior angles. So I'm going to say that angle C and angle D are congruent because they're alternate interior angles. Alternate interior angles will touch both the parallel lines and the transversal. Angle C is congruent to angle D by the alternate interior angles theorem. You could have done this proof by recognizing that A and E are congruent instead. That's also totally allowed. In fact, that's the way that you could do the proof in 3 steps. You wouldn't even need the vertical angles. But look what we got here, folks. We got our angle next to a side, next to an angle. And on the right triangle, we have an angle next to a side, next to an angle. We've just shown that these two triangles are congruent. ABD is congruent to EBC by the angle side angle congruence theorem, which we could just write as ASA. Nice. Now the second proof is going to be a little bit trickier. We are told that angle F and angle K are right angles, and that HF is parallel to GK. On this proof, we want to use both of our givens before we really look at the diagram too closely. F and K are right angles, but we didn't show that they're congruent. That requires a step. Angle F is congruent to angle K because of the right angle congruence theorem. Let's use the fact that these two lines are parallel, HF and GK. And once again, when you have parallel lines, look for a transversal that cuts between them, and you can make alternate interior angles. Be careful. The alternate interior angles are here on H and here on G, not the smaller angles down here. This smaller angle here doesn't actually touch the parallel sides, so these two would not count as alternate interior angles. I'm going to put them as X because I want to mark off that they are not alternate interior angles. But what can we call this angle here? Well, I'm going to call it FHG. Is congruent to, in our proof statement, F is congruent to K. So the first letter here is F, the first letter here has to be K. H is congruent to G, so I'm going to call this KG, and G is congruent to H, so I'm calling it H. This is using the alternate interior angles theorem. Last, most certainly not least, we have two angles that are congruent, but we need a little more. If we could show that a side is congruent, we'd be good. Thankfully, this side here, GH, is the same as this side here, HG. We can use the reflexive property to show that this side is congruent to itself. Why would we do that? Because now we would have angle, angle, side. Here we would have angle, angle, side. So we could say that HG is congruent to, again, based on the letters of our proof, GH. This is the reflexive property of segment congruence. And as said before, we now have an angle, and a side that are congruent. So triangle HFG is congruent to triangle GKH. Love it. For our last example, example 4 is all about filling in the blanks. I'm going to give you a couple pieces of information, And I'm going to tell you what theorem we need to use. You have to figure out what missing piece of information we would need to use this theorem. I'll show you the first one, and I want you to pause the video and see if you can do the rest. So, we're trying to prove that these two triangles are congruent by angle, angle, side. All we know is this. GH is congruent to MN, so we have a side that's congruent. Angle G is congruent to angle M. If we're trying to use the angle, angle, side theorem, we need two angles and one side. Well, we've got one angle and one side. So the last thing we need to show is an angle is congruent. But which angle do we pick? Well, if we picked H and N, think about what that would look like. An angle next to a side next to an angle. That would be the ASA congruence theorem, and we don't want that. So I'm going to pick angle F is congruent to angle L, because now we've got an angle next to an angle next to a side on both triangles that are congruent. We've made it work. Pause the video and see what you can do with the next couple of examples. How'd you do? These are how we could fill in the blanks to finish these statements. It's a pure coincidence that these end up being the same and these end up being the same. Genuinely didn't intend for that to happen. But these are all of the statements we would need in order to prove the theorems listed. Thank you so much for listening, everybody, and have a fantastic rest of your day.